Welcome to today's Explainer, where we're going to completely shatter absolutely everything you thought you knew about the scale of the universe. Okay, let's just dive right into this, because we all know that at the center of almost every galaxy lies a supermassive black hole, right? We even recently captured a photo of the one right in the middle of our very own Milky Way. But when you hear the word supermassive, what kind of scale pops into your head? Well, get ready, because the reality of these cosmic titans is far stranger and honestly way larger than you could possibly imagine. So the ultimate question we're tackling today is, how big can a black hole truly get in the universe? To figure that out, we have to start at home, but be prepared, because the final answer is going to leave you totally speechless. We're going on a cosmic zoom today, scaling all the way from the microscopic up to absolute monsters that literally break our understanding of physics. Let's actually do a quick reality check right here in our own cosmic backyard. The supermassive black hole at the center of our Milky Way, it's called Sagittarius A star, is actually 500 times smaller than our solar system. Seriously, if you placed it right here, it would only stretch from our sun to the asteroid belt. If you were looking at a wide shot of our entire solar system, Sagittarius A star would just be a tiny little dot. So if our local supermassive black hole is that small, what does a true cosmic giant actually look like? Section 1. Black holes have no limits. To understand just how big they can get, we first need to take a look at the physical limits of ordinary cosmic objects. You know, almost everything in the universe has a strict rulebook, a maximum capacity, but black holes, they play by entirely different rules. For instance, a planet can only get to about 10 times the mass of Jupiter. Any bigger than that, and its own gravity squeezes it so intensely that it ignites and turns into a star. But stars have limits too, known as the Eddington limit. A star can really only reach about 250 to 300 times the mass of our sun, before it just collapses under its own gravity, turning into either a neutron star or, you guessed it, a black hole. But here is the crazy part. The black hole limit, it's infinite, literally infinite. According to modern physics, a black hole is the only single-body object out there with absolutely no physical size cap. The only thing limiting its monstrous growth is the age of the universe itself. They haven't reached their maximum size simply because they just haven't had enough time yet to absorb all the surrounding matter. Given enough time, they can grow 10 times, 100 times, even 1,000 times larger. Which brings us to Section 2, primordial black holes and the mystery of dark matter. Logically, if these things constantly grow over time, the oldest black holes should be the biggest, right? Well, let's rewind. So back in 1971, the brilliant Stephen Hawking threw out this wild idea about primordial black holes. He believed these were born in the brief, frantic nanoseconds right after the Big Bang, a time when matter and energy were essentially the exact same thing. These black holes were formed purely from the collapse of pure energy, long before the first atoms even formed 380,000 years later. Now, these primordial black holes would be mind-bendingly dense. Think about a single microscopic proton. A black hole that size would weigh as much as Mount Everest. And a black hole the size of a small 25 paisa coin, that would generate a gravitational pull equivalent to the entire Earth. It could literally force the moon to orbit it. These microscopic anomalies are so incredibly dense, it's led some astronomers to believe they might actually be the mysterious dark matter influencing our universe. It's an absolutely fascinating hypothesis, though we're still waiting for telescopes like James Webb or Hubble to prove it for sure. Okay, moving up the scale, Section 3, the world of stellar black holes. This is the realm we have actually proven to exist, born when massive stars cross that physical limit we talked about earlier and violently collapse. So the absolute smallest stellar black holes we've actually found, they're a mere 17.2 kilometers wide. Just think about that for a second. That is unbelievably small for something packing such terrifying cosmic power. To put that into perspective, you could easily fit 3 of those side by side right inside the city of New Delhi. Yet it is just mind-blowing that something small enough to fit inside a single city can easily command a massive red giant star. In fact, one of these tiny 17-kilometer black holes currently controls a red giant named V723 Mon, which is 24 times larger than our sun. Now let's look at the absolute apex predator of this weight class. At the top of the stellar category is M33X7, the largest known stellar black hole. It's only 92 kilometers wide, but man, it has a voracious appetite. It's currently and very violently ripping apart a massive 70 solar mass blue giant star. And the friction from all that star material being sucked in, it creates blinding heat, emitting light that is 500,000 times brighter than our sun. But here's the catch. Stellar black holes kind of hit a ceiling at about 150 solar masses. Why? Well, because they're born from stars. And as we know, stars themselves have a size limit. But wait a minute. If stellar black holes max out at 150 solar masses, how on earth do we explain the supermassive black holes at the center of galaxies that weigh millions of times our sun? It leaves this massive evolutionary gap in our understanding. This leads us right into section 4, from quasi-stars to supermassive. So how does the universe jump from a 150 solar mass cap all the way to black holes weighing millions of suns? So, astronomers theorize this massive gap was bridged by something totally bizarre in the early universe, called quasi-stars. Back when the universe was incredibly dense, a massive star could absorb over 1,000 times the mass of our sun. But before the star could even fully form, its gravity became so intense that its core collapsed into an Earth-sized black hole. So picture this. You've got a star on the outside, but a black hole on the inside. A massive cosmic tug-of-war happens next. The intense heat pushes outward, while the black hole pulls inward. Eventually, the black hole just eats this quasi-star right from the inside out. It's believed these crazy Earth-sized black holes eventually merge together to become the supermassive giants we see today. Actually, speaking of supermassive black holes, we really need to bust a common myth right now. Because these things sit at the center of galaxies, we often assume their gravity holds the whole galaxy together, right? I mean, kind of like how our sun holds the solar system together, since it accounts for 99.86% of its mass. But here's the reality check. Our central black hole, Sagittarius A, holds only 0.001% of the Milky Way's total mass. It is not holding our galaxy together. As we touched on earlier, it's very likely dark matter, maybe even those microscopic primordial black holes, that is actually holding the whole shebang intact. All right, brace yourselves. Section 5, ultramassive monsters, and specifically TON 1618. We've gone from the microscopic to the stellar to the supermassive. Now it is time to scale up to the absolute pinnacle of cosmic terrors, the ultramassive black holes. So, way out in the galaxy, OJ 287, roughly 3.5 billion light-years away, there is a black hole so incredibly large that you could fit 3 of our entire solar systems inside of it. Just think about that. But as massive as that is, compared to the universe's biggest known monster, it is practically nothing. The biggest one makes the black hole in OJ 287 look like a tiny human standing next to a towering mountain. Enter TON 618. This thing is an ultra-massive titan weighing in at a staggering 66 billion solar masses. It possesses an accretion disk that is brighter than 100 trillion stars combined. It's located 18 billion light-years away from us, which means the image and data we study of it are actually 10 billion years old. Who even knows how much bigger it's grown in the 8 billion years since that light left it? To really wrap your head around this scale, just imagine this. If you fell into TON 618 and you were traveling at the absolute maximum speed limit of the universe, the speed of light, you would be traveling for a full entire week before you finally hit the center. 1 whole week, moving at 300,000 kilometers per second, just to cross a single object. And that brings us to a really mind-bending conclusion. We know that the actual core of a black hole is a singularity, right? An infinitely dense, zero-dimensional point. But the part we measure, the part that takes a week to cross at light speed, is the event horizon, the boundary of no return. So it leaves us with one final, pretty awe-inspiring question. How should we truly measure the size of the most mysterious objects in our universe? By the invisible boundary of their reach, or by the infinitely tiny dot at their core? Take that thought with you today, and keep looking up.